Of significance, one population mean where sigma is unknown, two population means that's the matched pairs case, then also two population means independent samples, that's number 4, but mixed in there is one population proportion, two population proportions, chi-square, and linear regression t-tests, as well as what's called an Anova. One-way Anova is an analysis of variance, right? So it's a way of determining the relationship between more than two means by analyzing the variances of the data set. Right? But it's a little beyond at this point. Right now we have to get into the notation. Notation can be a little tricky things, but it's consistent, so it becomes more manageable. Right? So once you get used to what the notation is talking about, then everything else kind of works itself out. Right? So we have null and alternative hypotheses. We abbreviate the null hypothesis with a H sub 0. All right, so that's typically the default hypothesis, or I mean, I could just read it, either the statement that's being tested or some understood or accepted value for the population parameter. All right, so in the case of, trying to remember, I think it was a library where a poll was conducted to see if a new library should be built. We made the assumption that the population proportion would be 0.5 because you have a 50-50 chance of selecting, if it's completely by random, 50-50 chance to select one of the two outcomes, either for the library or against the library. Now, context may tell a different story, but in the absence of that additional information or context, we would just default to a 0.5. Right? When it comes to means, it's a little trickier because sometimes there isn't a default value, but usually the question will kind of clue you in on what you should use as your null hypothesis in the case of a population mean. Sometimes it's in the context of the problem and it kind of jumps out at you. So if they say, for example, test the claim that gas prices are statistically significantly higher now than they were in December, then you can say, okay, well, let me go find out what the average gas price was in December and use that as my null hypothesis. I'll just assume that that's what it was, and then we have something to compare to and against. All right, the alternative hypothesis is the statement that's true when the null is not. All right, that the whole point behind a hypothesis test is to make a decision between the null and alternative hypotheses. Common notation for alternative hypothesis, H sub 1 and H sub A. All right, we're going to use H sub A. Right? I think it's a little more obvious what we're talking about when I say H sub A versus H sub 1. All right, the significance level, we've talked about that almost ad nauseum. The most common ones are 0.10, 0.05, and 0.01. Those are consistent with the confidence levels that we use for confidence testing. So 0.99 or 99% confidence interval estimate would correspond with a 0.01 hypothesis test alpha value. All right, so they play the same role. It's just you're kind of looking at them as complementary values instead of just looking at the confidence level and working your way from there. All right, so it's more of an intuitive thing. As you go forward, you start to realize that the 0.10 and the 90% are really telling you the same thing. All right, when you're dealing with a confidence interval or a hypothesis test. All right. Significance in a hypothesis test is not, this is a very important statement, does not always mean that there's a strong effect, just strong evidence of some effect. All right, so if we have a null and alternative hypothesis value, let's say, for example, you have HO is that the population proportion is equal to 0.5, and HA where the population proportion would be greater than 0.5. So the alternative hypothesis is always going to have some form of inequality, right? Because if the alternative is really everything that the null is not, then I would say, all right, well, what's the opposite of equals? Not equals. All right, but how many ways can you represent not equals? You could talk about being greater than, being less than. Or if you have no idea, you just know that they're not the same. Like, for example, I don't think that the population proportion is 0.5, But I don't know until I start collecting data whether I would consider it to be greater than 0.5 or less than 0.5. I would just simply use a not equal to symbol. All right. But this highlighted statement, significance in a hypothesis test, does not always mean that there's a strong effect, only that there's strong evidence of some effect of the imposed treatment. So if I conduct the entire hypothesis test and I determine, for example, that the null was incorrect and the alternative was correct, I'm not saying that it's going to be way more than 0.5. All right? The alternative is just saying that it's simply more likely that the population proportion is more than 0.5 than it is for the population proportion to be exactly 0.5. Right? But it doesn't speak to how much more than 0.5. Right? It could be 0.501. It could also be like 0.999. Right? It could be wildly different, or it could be only minutely different, and everything in between. The hypothesis test just allows us to make a decision between these two possibilities, but it doesn't really get into how far along that alternative hypothesis you would be. Like, for example, like what I was saying, 0.501 as opposed to 0.999. Right? It's not going to allow us to distinguish between those two. It's just going to allow us to determine that the alternative is more likely to be true than the null. All right. Just like confidence intervals, if you don't like the conclusion, you can start playing around with the alpha value. Yeah. So we do a 99% confidence interval estimate. It's a fairly wide interval. Right, depending on the nature of the situation. Comparatively, it's wider than 0.95 or 0.90. All right. So if you do a 0.9 confidence interval and you don't capture the value that you're looking to capture, the way to make the interval wider would be to increase your confidence level. Right? So you're just going to capture more information. It's the same idea here. If you don't like the conclusion and you went with a 0.10, you can reduce and maybe make it a 0.05, or you can go the other way around. Right? We'll need to know what we're comparing to the alpha values in order to really understand what I'm saying. But that's something that you could always do if you don't like the outcome of your test. The power of a test is the ease in which you can reject the null hypothesis. All right. So the easier it is to reject the null, the more power the test has. All right. So if we want to increase the power of the test, the ease in which we can reject the null hypothesis, we can increase alpha, or we can increase the sample size. Increasing the sample size reduces your standard error. It reduces your standard deviation. Notation-wise, this is actually, I can't believe this. I've been working off the same document for like the last 20 years, and I never noticed this. If we increase the sample size, that doesn't impact the population standard deviation. It'll decrease the sample standard deviation. So that should be S. I can't believe I didn't notice that. All right. Increasing the sample size decreases S. Let me get rid of thus. That's a little pretentious. While I'm at it making my edits, decreases the S, and therefore S over the square root of N decreases. All right. So that'll tighten your interval, your confidence interval, if that's something you're doing. But it'll also make it easier to reject a null hypothesis. The reason it tightens up the interval is because S over the square root of N is your standard error. That's going to, the smaller the standard error, the smaller your margin of error, the plus minus value, the smaller your interval. All right. Type 1 and type 2 errors, you're going to need to know these. All right. It's always on the AP. It'll be on my test. Just identifying under what circumstances you're dealing with a type 1 and type 2 error. All right. Type 2 is the more egregious one. All right. That's the worst possible case. The type 2 error, that's just simply bad. Right? It's not, neither of them are good because they're both forms of error. But the type 1 is the worst one. All right, and that's because if we're thinking of the null hypothesis as some sort of statement of the status quo, then we would have to have a lot of evidence to move us off of that. Right? So if you're contesting some long-standing rule or belief, you better have some really good evidence if you're going to conclude that that long-standing rule or belief is incorrect. You know, just a simple case, the school day starts, what, 8 o'clock-ish? Depending on what time you get here, I guess. Maybe if you have first period off, maybe it's a little later. But if I'm conducting a study, and so the school day it begins at 8 o'clock, and it has begun at 8 o'clock for years, right? But if I'm conducting a study to say, you know what, high school students need to come in later. Elementary school students should come in earlier. That's I mean, I'm sure you've heard that before. Like, the elementary school students would be fine at an obscenely early hour. But the high school students, I mean, if they told you had to come in at 7 o'clock in the morning, you'd be like, what? Why? What did we do? Whose feelings did we hurt? You know, it would be some terrible thing. But elementary school students are like, I'm up at 5 o'clock anyway playing with Legos, so I might as well do that at school, you know? So if I'm collecting data to move us off of that 8 a.m., that's going to have a trickle-down effect impacting every aspect of the school district. Right? High school students come in later, so elementary school students come in earlier. Where do the middle school students fit in all of this? You know, it would be a massive overhaul of the system. It would be a complete change. Right? So if I screw that up, so if I draw a conclusion that 8 o'clock is too early for high school students, and I'm wrong, you've just changed the entire district and the way the district operates based off of a mistake. Right? That's awful. All right, now if I go the other way, and so the long-standing rule or belief is 8 a.m., and I come up with information that says, no, that's right, that 8 a.m. is fine, we're going to keep things that way. Right? We didn't change anything. It's still incorrect. It's still an incorrect conclusion, but there was no trickle-down effect. There was no change made. Right? The long-standing rule or belief is still in place. Even though it's incorrect, you haven't made any monumental changes to the system. Right? So correcting that mistake later on is not going to be a big deal because you haven't made a change yet. Right? Any instance where you would make a change and then have to go back and correct all that, that could be awful. All right? So I put this little blurb in there. Think, type 1 error, false alarm. All right, researcher thinks that they discovered a difference, but there is none. All right, type 2 error is a missed opportunity. Researcher fails to detect the difference that is present. All right, it's an oversimplification of the idea, but it gets the point across. All right. The traditional approach, we're going to learn 2 methods for conducting hypothesis tests, and those 2 methods, if you read in the textbook or whatever, they're kind of distinct from one another, as in you could do it this way or that way. What we're going to do is take those 2 methods and combine them into one method. All right, so we have the traditional approach and we have the p-value approach. All right, the traditional approach utilizes your alternative hypothesis, a cutoff z-value or t-value, and how your, what we call a test statistic, corresponds to a graph. That'll allow us to draw a conclusion. All right, the shaded region of any of these graphs, I don't like the equal signs anymore here. It's confusing. So that's another typo for somebody. I'll do parentheses. All right. The shaded region is what some people call the rejection region or rejection area. What that means is that if your test statistic falls in this shaded region, all right, this is the rejection region, then we would reject the null hypothesis. So reject HO if your test statistic lands in this region. All right. Now I haven't shown you how to compute a test statistic, so it's like, okay, it's a number. It's some kind of number. All right. So what we'll have is a critical value, abbreviated CV, surprisingly. I'll put it in terms of Z for now. So we'll have a critical Z value that represents the cutoff between the region of the graph that doesn't correspond with the rejection of the null hypothesis and the region of the graph that does. Right? So when we compute our test statistic, if the test statistic falls in this region here, we would reject the null hypothesis. Right? That's for a right-tailed test. Right-tailed tests correspond with the alternative hypothesis that uses a greater than symbol. Right? So if there's a greater than symbol in your alternative hypothesis, that corresponds to a right-tailed test. If there's a less than symbol, that corresponds to a left-tailed test. Same setup, you would still determine a cutoff or a critical value. And if your test statistic falls in that shaded region based off of the cutoff value, then you would reject the null hypothesis. All right. Tests involving an alternative that uses a not equal to symbol. Not equal to symbol could mean that you don't know if it's greater than or less than, but you know it's one of those two. All right, so the not equal to symbol is thought of as greater than or less than. All right, so we account for both of them. All right, so the greater than corresponds with the right-tailed test. The less than corresponds with the left-tailed test. So we just put them all together. All right, so we'll get two critical values here. All right, so we have two potential regions for which we could reject the null hypothesis. If our test statistic falls in either of these shaded regions, we would reject the null. All right. The test statistic varies by test, depending on the method that you're using. It's and the method is determined based off of the context of the problem. But it could be a z-test involving a z-distribution, t-distribution, and then when we get to it, a chi-squared distribution and an f distribution for the Anova. All right, so it's like, oh, great. It varies by the test. So that means we're going to have to know about 5 different formulas. Right? Not really. I'll show you ways around it. But it will change from test to test, and so you'd have to make that adjustment. All right. Generally speaking, it's the distance the observed score is away from the expected score in terms of standard errors. All right. So as a general rule of thumb, we would say, and it could be z, it could be t, it could be chi-squared, but let's say it's z because that's what we've been working with. We would be looking for the difference between the statistic and the parameter. So statistic minus parameter over the standard error. And the standard error is one of the things that varies by process. All right. But it would be the same standard error that you use in a confidence interval. All right. So sigma over the square root of n, s over the square root of n, the square root of pq over n. Then if you get into the two population stuff, gets a little bit more complicated, but like the square root of p1q1 over n1 plus the plus p2q2 over n2. All right, with or without hats, with or without bars, it could get a little crazy. I'll talk to you more about the AP formula sheet and how it sort of gives you the recipe to build these formulas on your own. So it's not like you'll have to fully memorize them. You'll just have to know how to navigate that reference sheet. The p-value approach is a little bit more complicated because if you're doing this by hand, and we will, you're going to need to determine test statistics first. So you have to do all the stuff in the traditional method and then convert that test statistic into a probability value, p-value, probability value. So the benefit of this is it's easy to draw a conclusion based off of that p-value. If the p-value is less than your alpha value, then you reject the null hypothesis. Right? It's as simple as that. The problem is it takes a little doing to get you to a point where you have a p-value. But if I tell you that the p-value is 0.00592, and I tell you the alpha value in the problem is 0.05, the p-value is going to be less than the alpha value. That would tell me to reject the null hypothesis, whatever it is. If you reject the null hypothesis, that means you're accepting the alternative hypothesis. Right? Now, in terms of theory, I mean, you could read through this, but it's basically an innocent until proven guilty kind of thing. But when you're dealing with confidence intervals, hypothesis tests, any sort of methods of inference, you're really kind of getting into what would happen if there was no effect based off of any kind of catalyst, right? So it's basically if probability and nature and randomness were allowed to work the way they work, what would you expect to happen? All right. And so if you get something different from what you would expect to happen based off random chance, we call that significance. All right. So if I tell you, okay, I think the probability of getting heads when I flip a coin, because I think it's a trick coin, is 0.8. All right. Pretty sizable deviation from what you would expect. You would expect it to be 0.5, in the neighborhood of 0.5. So what a hypothesis test will do is it'll run through the simulation behind the scenes based off of standard errors and things like that. It's going to determine what the likeliest probability would be if it were a fair coin. So if you flipped a fair coin a bunch of times, what would that project out into the population? Maybe you get an interval of like 0.48 to 0.52, right? So that interval is the likeliest set of outcomes, right, based off of the chosen level of confidence. Play around with the level of confidence, you can increase or decrease the size of the interval. But if my 0.8, my suspected value of this trick coin of 0.8 falls in that interval, then it's not showing a significant difference from what would happen with an ordinary coin under ordinary circumstances. Right? But if my 0.8 does not fall in the interval, we're saying that based off random chance alone, this is what we should have got, 0.48 to 0.52. But when I did it with this coin, I got 0.8. Right? First, I checked to make sure that there wasn't any unnecessary bias. Maybe it was the way I was flipping the coin that led to a particular outcome. But if all that stuff is accounted for, then we can determine or conclude that the probability of flipping this coin as many times as like you do it infinitely many times. I mean, not practically speaking, but you can do it many times over and over again. We would say that this is not a fair coin, right? Because it doesn't fall in the interval. The same idea happens when you're dealing with a hypothesis test, except we're looking for a probability value associated with that outcome of 0.8, which is really just saying what are the chances of getting 0.8 if I were to flip the coin many times, a fair coin many times, what would be the probability of getting a 0.8 as an outcome? All right. If it's very small, we're saying it's not likely. If I get a probability value of 0.8 being the true outcome, and that probability is like 0.000592, I'm saying that the chances that 0.8 is correct is so remote that we would have to dismiss that. We'd have to say, well, there's no way the 0.8 is true, so it must be something else. All right? You could do it with 0.5, you could do it with whatever probability value makes sense, or I'm sorry, population proportion makes sense. And then that is how we would draw the conclusion. But, there's a lot going on here because you can see the solved examples got, well, surprisingly the 0.8, but different context. But you could read through this. I'm going to take you through one from beginning to end. Yeah, because I wanted to do one with a coin. So Zach and Greg are flipping a coin and betting on the results of heads or tails. Zach gets $1 from Greg whenever heads comes up, and Greg gets $1 from Zach whenever tails comes up. All right, so it looks like it's, in terms of payout odds, it looks like it's just a one-to-one situation. At the end of 50 flips, Zach is down $10. In other words, there are 20 heads and 30 tails in the 50 flips. You know, the ordering could vary, but if you're just counting them up, that seems to be what happened. Zach suspects that he's getting cheated. He thinks that the coin is not balanced and the proportion of heads is less than 0.5. So we do the hypothesis test. All right. So the first step would be to state the null and alternative hypotheses. So the HO and the HA. All right. The null hypothesis would be the long-standing rule or belief. All right. We're talking about a coin. Coin has two sides. You have a 1 in 2 chance of getting one of those two sides, assuming it's a fair coin. I would say that the probability or the population proportion would be 0.5. All right, that's my long-standing rule or belief. I'm going to assume that the coin is fair, all right? Because every other time I flipped a coin, that's how it played out. So why would this coin be any different? All right. Alternatively, we would say that the population proportion of heads is less than 0.5. And that's because they just flat out said it there. Population proportion of heads is less than 0.5. That's what we're looking to test. So that's got to be one of our hypotheses. What they're asking should be either your null or alternative hypothesis. All right. So we draw a picture. Normal distribution. It's going to be left tail shaded in because the alternative hypothesis is a less than symbol. All right, so this would be my rejection region. Let me try to shade it with the... Oh, this is going to look awful. Best I can do. All right, so it's the left tail that gets shaded in because the inequality is pointing to the left. I mean, you could look at it that way. All right. Now, they said to do this with an alpha of 0.05. All right, the alpha 0.05 is the area contained within that bounded region. So what I would need to do is find a critical z-value corresponding to an area of 0.05 to the left-hand side. All right, so that brings the calculator into the party. Get out of here. So you compute this value by using second var's inverse norm, option 3. All right, that's the case where you're given areas and you need a z-statistic, or in this case, a z-score. Put in your area, 0.05. We're going with the standard normal curve, so mu and sigma should be 0 and 1 respectively. Paste it in, hit enter, and now we have negative 1.645 as my cutoff. All right, so that's the number that represents the boundary between the shaded rejection region and the non-shaded non-rejection region. All right, so we're going to compute a test statistic, and that test statistic is going to give us a number. All right, since it's a normal distribution, it's centered around 0. So this basically becomes a glorified number line. All right, so anything larger as a test statistic, anything larger than negative 1.645 is going to fail to reject the null hypothesis. Anything less than that, so further in the negative direction, would allow us to reject the null hypothesis. So we need a test statistic. All right. So again, it's statistic minus parameter. So my z-score in this case, because we're talking about population proportions, sample proportion is abbreviated with a p hat. Population proportion is p. And then the standard error is the square root of p q over n. But it could also be if you have no sense of what the population proportion is, or you think that there's no way that that's going to be true, the 0.5, you can go with p hat q hat over n. but that's a little bit more rare. All right, so we'll use PQ over N. All right, so that's the part of the confidence interval formula. And actually, when you really think about it, we're doing a lot of stuff that we would do for a confidence interval, just in a different order. You know, because the confidence interval formula, I'll just jot it down here, was P hat plus or minus E, which was Z alpha over 2, times the square root of P hat, PQ over N, possibly with or without hats. All right, so it's got the same ingredients. We found a Z-score. We need to find P hat. We need the square root of PQ over N. We're just using this to find a Z-score rather than finding an interval. All right, so computationally, we pretty much have everything we need. We need to pull that P hat. All right, P hat is X over N. All right, so we had a sample of 50 trials. And heads came up 20 out of the 50 times. All right, we just pulled that from the wording of the problem. All right, 20 successes, 50 trials. You can go decimal on that because it's a clean decimal. All right, so 20 out of 50 would be 40% or 0.4. So my test statistic is going to be 0.4 minus the assumed value for P. Let's see here. I got my color scheme all out of whack here. Hold on. Yeah, okay. Minus the population parameter, or the assumed population parameter, which would be 0.5. That's our benchmark. That's our cutoff. So 0.4 minus 0.5 over the square root of PQ over N. So P is 0.5, or assumed to be 0.5. Q is 1 minus P, so also 0.5. And the N value, they said there were 50 trials, so N value is 50. All right. So we're going to crunch these numbers. I'm just going to cover this up. So you do it as a fraction, alpha y equals N over D. 0.4 minus 0.5, you probably do that in your head, but I'll just do it out. The square root of another fraction, alpha y equals N over D. 0.5 times 0.5, again, something you probably do in your head, but let's just do it this way. Over 50. Enter, and you get negative 1.414. All right, so, I mean, this is a made-up problem, but you know, you can get some funky decimals. It's just not very often that you would look at this and say, hey, that's the square root of 2. Or negative anyway. You know, that's not typical. So expect hideous numbers when it comes to test statistics and p-values. All right, so now what we do is we look at this test statistic on the graph that we've already created. Negative 1.414. I don't know precisely where that's going to be, but I do know it's going to be shy of the rejection region. So I'll just place it right here for the heck of it. So Z equals negative 1.414 would be right. I mean, I guess, well, anywhere over here would have been fine, but it feels like it would be pretty close to the negative 1.645, just not quite, right? Now, in terms of conclusions, it's not in the shaded rejection region, right? The shaded rejection region always speaks to the null hypothesis. So this is saying do not reject the null hypothesis, right? So if I'm not rejecting it, I'm keeping it. All right, so the null hypothesis is more true than the alternative. But if I had a wider rejection region, that was just a smidge more to the right, then I could get the exact opposite outcome, the exact opposite conclusion. And the way we can make that happen is just make our alpha value, instead of 0.05, make it 0.10. That would give you more area, shoving your critical z value to the right, possibly covering the test statistic. All right? So then what we would need to do is compute the p-value. All right? And so for the p-value, we rely on the alternative hypothesis. This is saying the left side of the graph. All right? It's a left-tailed test, left side of the graph. What I would be looking for is the probability that the z-value is less than this benchmark. All right, so this region here. So that is probability that z is less than the negative 1.414. All right, so in my calculator, I want to hang on to the most accurate form of the negative 1.414, which I have here. I'll call that z. So now every time I hit z, that's going to come up. If I'm looking for the area to the left of this, that's a normal CDF situation. So second vars, normal CDF. I want to go from negative infinity, well, the calculator just goes negative 1 times 10 to the 99th power, to the z value that we just came up with. And we get 0.0786. All right. The p-value, if it's less than the alpha value, you reject the null hypothesis. That's not the case here. All right. So p-value, or p, just the letter p, is greater than alpha. So we do not reject the null hypothesis. Do not, no, I wrote donut. Reject HO. We'll continue with this tomorrow. So we got to the point where we computed the p-value. Now it's just a matter of drawing the conclusion. So we know that we're not rejecting the null hypothesis, which means that that's the one we're keeping. We just have to formulate the conclusion appropriately. All right. So there's a templated approach that we use just for consistency in writing conclusions when it comes to hypothesis tests, but also for confidence intervals. But you know, we generally don't want to deviate from this too much. As long as what you say is logically equivalent to this templated response, then you're okay. The problem is it almost never is when people deviate from what I'm about to show you. So there are rare circumstances where somebody can get the logic right, but it's a couple of, you know, it's conditional relationships. So if you're not up to snuff on propositional logic, you could run into some trouble. So we say there is insufficient evidence to reject the claim that, all right, and so we state the null hypothesis in words. All right, so the null hypothesis was p equals 0.5. P represented the population proportion of heads. All right, so we're saying there's insufficient evidence to reject the claim that the population proportion, bless you,
Thank you.
of heads is 0.5 at the whatever significance level, in this case 0.05. All right, and so that addresses the null hypothesis, but it doesn't address the question that was being asked. All right, they said to test the claim that the population proportion of heads is less than 0.5, so we have to address that. All right, if I can get this lasso thing to work. All right, so we would follow that up by saying, therefore, the claim that well, you wouldn't necessarily have to repeat everything, but we're really saying the population proportion of heads is less than 0.5. Or the claim that it is less than 0.5 is false. All right. So, I mean, there's a lot going on in that response, but if you stick to that general framework, then you'll get an appropriately framed conclusion. So we start off with whether it's sufficient or insufficient evidence. All right. So this is the first decision that you make, because we're always talking about whether we are rejecting the null hypothesis. So based off of my conclusions over here, determined by the p-values, I could say that I would have sufficient evidence to reject the null or insufficient evidence to reject the null. All right, we're always talking about whether we have sufficient evidence to reject, specifically reject. We don't say support, we say reject. The claim that, and we state the null hypothesis in words. And then we state the alpha value, and then we follow that up by actually answering the question. All right, so the first sentence always addresses the null hypothesis. All right, it happens all the time. People, they don't believe me until you turn in an exit ticket or an assessment and you lose credit for that, and you're like, what happened? This looks fine, and like the logic doesn't follow. All right, so you change the phrasing of it, and because of that, you run into a propositional logical contradiction. Oftentimes it's really just a simple matter of, I don't know if you've heard the terms converse, inverse, contrapositive. Those are, they used to be taught in lower levels of math with like truth tables and logic proofs and things like that. It used to actually be in the geometry course, but it doesn't always get taught.
I feel like some of us were supposed to learn that in algebra. We were supposed to do like a logic unit, and then COVID happened, so we didn't really learn anything.
That might have been the case, yeah. But if you have a conditional sentence, like, if it is sunny out, then it will be warm. I don't know. If it is sunny out, I will wear shorts. If it is sunny out, like whatever you can think of. Swapping the premise and the conclusion doesn't lead to logical equivalence. Right? So if I have, like, if it is sunny out, then I will wear shorts. If I change that around and say, if I am wearing shorts, then it is sunny out. Well, not necessarily. I could choose to wear shorts just for the heck of it. So you run into that kind of problem when it comes to conclusion writing. If you deviate from the template, then you could end up with something that isn't logically equivalent. This isn't really as complicated because we're talking about double negatives and things like that, but it is enough of a concern that I strenuously suggest that people just stick to the template. All right, so there is either insufficient or sufficient evidence to reject the claim that, and then you state the null hypothesis in words at the 0.0 whatever, maybe it's 0.01, maybe it's 0.10 significance level, and then the second sentence, all bets are off, you just answer the question. All right. So looking at number 3, USA Today reported in 1992 that 39% of all elementary school children claim that when they grow up, they want to do something to help other people. However, in 1995, pretty vague, in 1995, 128 of a sample of 317 of these same children claimed that when they grow up, they want to do something to help other people. So same question, just percentages may be a little bit different, we'll see. Does this information indicate that there has been an attitude change either way? Right? So what we're looking to make a determination on is the true population proportion percentage or population proportion of individuals who want to help people when they grow up. All right, so my null hypothesis would be the status quo. So we would establish 39% as the status quo. All right, that's the long-standing rule or belief. It's not that long-standing, but that's what we're comparing against. All right, we have information that suggests that it's not just a 50-50 situation. All right, so my default is that p is equal to 0.39. Alternatively, there's been an attitude change either way. That would just say that the population proportion may just simply not be equal to 0.39. All right, I don't know which way. I mean, this sample of data might give me an indication, but it's just one sample of information. Right? So going into the framework here, we wouldn't necessarily make an assumption one way or the other. All right, so I'm going to draw a normal curve, normal distribution. It's going to be a two-tailed situation. All right, two-tailed because it's a not equal symbol, but more importantly, not equal could be greater than or less than, so that puts you on the left tail or the right tail. So I need critical z-values. All right, the alpha value can be whatever we want it to be because they didn't indicate. So I'm going to let alpha be equal to 0.05. So each tail is going to have an alpha over 2 equal to 0.025. Right, because we're splitting that alpha evenly over the two sides. All right, so I need my critical z-values. Bring the calculator into the party. So that's inverse norm, second, vars. The AP doesn't want to see calculator verbiage or lingo. Just the result is all they care about. All right, so the area 0.025. So we're looking at negative 1.96 approximately. Symmetry tells me that the other side would be positive 1.96. Those are my cutoffs. If my test statistic is less than the negative 1.96 or greater than the positive 1.96, then I would reject the null hypothesis. So I need my test statistic. All right, same formula as yesterday. All right, so difference between the sample and the parameter divided by the standard error, square root of PQ over N. All right, we go with the default value unless we have some reason to deviate from that. All right, so it's just the same rule again. All right, so the p hat, the sample of information that they gave us, 128 successes in a sample size of 317. So p hat is going to be 128 over 317, x over n. All right, doesn't look like it's going to be too beneficial to put that in decimal form, so I'm going to leave it as is. All right, so 128 over 317 minus 0.39 over the square root of 0.39. Q is 1 minus P, so times 0.61 over the sample size, which would be 317. So we'll crunch these numbers. All right, I'm going to hang on to my critical z-value. All right, I just want to at least be aware of that in its truest decimal form, because you never know. It could be one of those borderline values that we get as a test statistic. You don't have to save it. You just got to have access to the full-blown decimal value. All right, it's very rare that it happens, but it technically could be a possibility that you could get a test statistic that's like negative 1.96115. You know, and a bunch of decimals after that. They would both round to negative 1.96, but the test statistic would fall in the shaded region based off of the pure decimal value. So just at least hang on to this in the calculator so we know what the true value is. All right. So alpha y equals n over d. Another alpha y equals n over d. 128 over 317 minus 0.39 divided by the square root. Another alpha y equals n over d. 0.39 times 0.61 over 317. All in one shot in the calculator. I don't have to worry about intermediate rounding steps. I get about 0.503. All right, that's nowhere near the negative 1.96, so I'm not concerned. All right, so now I can kind of disregard that negative 1.59, blah blah blah. All right, so if we compare this to the graph, I don't know why it does that. If I compare this to the graph, we know 0 is in the middle because it's a standard normal curve. If we're counting in 1 unit increments, we can get a better idea, but it really doesn't necessarily have to be like that, because if you know that 1.96 is about roughly 2, 0.5 is going to be a quarter of that, so quarter of the distance between 0 and 1.96 roughly. That's going to put my test statistic here. I'll just label that TS for test statistic. All right, that's not in the shaded rejection region, so I would not reject the null hypothesis. So I'd hang on to the null, ditch the alternative. All right, but I want the p-value, right, because that's going to tell me whether it would reject under other circumstances, like if I had selected an alpha value of 0.10 or 0.01. The p-value is helpful in making that determination. So the p-value we're looking for the z-score, or the probability that z is going to be greater than 0.503. All right. Now, we kind of run into a little bit of a, it's not much of an issue. It's just that since we split the alpha value up, we want to make sure we're comparing this result to the right number, all right? So there's two ways to handle that. One would be to get this p-value and double it and compare it to the 0.05. The other approach would be to take this number and compare it to the area associated with the shaded region that's relevant to this particular value, all right? So normally we say if p is less than alpha, we would reject the null hypothesis, all right? But in this case, since the rejection regions are alpha over 2, I would determine my conclusion, reject, not reject, based on the relationship of this p-value and alpha over 2, all right? So in the calculator, I need the number. I'm going to hang on to this. I'm going to store it in as z. So second, vars, normal CDF. My lower bound would be the z value that we just determined. The upper value would be something big, 1E99 if you want. Or you could just actually put some really large number in there. All right, but I'll do the 1E99. All right, paste it in. It gives you about 0.307. All right, and again, because it's a split rejection area, you have two possibilities. If this p-value is less than alpha over 2, we would reject the null hypothesis. Or we could say if 2p is less than alpha, we could reject the null hypothesis. It's the same relationship, just one of them allows you to work with the pure alpha value. So either way, it's not going to reject because that p-value is not, it's nowhere near 0.05. It's much, much larger. There's no way it's less than the alpha value or even the alpha over 2 value. All right, so we would say do not reject the null hypothesis. All right. All right, this looks weird. All right, so then we just have to write our conclusion. And I left myself no room to do that, so resize. So we're going to say that there is insufficient evidence to reject the claim that, and then we state the null hypothesis in words. All right, so there is, I still don't have a good place to write this. Let me just move this over. There is insufficient evidence to reject the claim that the population proportion it's a little wordy because that 0.39, that's the percent of all elementary school students that said when they grow up they want to help other people. No, I don't want to write all of that, so we'll paraphrase. The claim that the population proportion of students who want to help people is 0.39 at the 0.05 significance level. All right, so that addresses the null hypothesis. Our first sentence always addresses the null hypothesis. The second sentence answers the question. Does this information indicate that there has been an attitude change either way? Therefore, the claim that there has been an attitude change either way is false. Hold on, I gotta zoom in. So easily the most tedious part of the process, but it's the whole reason why we do this. Right? Because we know that on the sample level, that we have a particular ratio, proportion, however you want to think of it. We just want to know how that projects out to the population. Right? So that 128 over 317, that's about 0.4, 0.41 in that neighborhood, which is a value that's more than the 0.39. Is that far enough away from the previous percentage that we would say that that previous percentage was incorrect? All right. And so based off of this hypothesis test, which is based off the same concepts associated with the confidence intervals, it's saying no, that's not the case. Then we get to testing a claim about a mean. There's two scenarios there. The case where you know the population standard deviation and the case where you don't. All right, but it's all going to come down to the same general process. Identify null and alternative hypotheses using the correct notation. Create a diagram. Right, normal distribution or t-distribution as it might apply. Come up with a test statistic, the p-value, and draw a conclusion. Right? Calculator has hypothesis tests built into it. Right? So this test that we just did was a one population proportion hypothesis test. The issue with the calculator, I can just show you. So if you go to stat, test, it would be a one prop z-test, one population proportion z-test. All right. You'd put in your values. The p sub 0 would be the null hypothesis, the value that you used in a null hypothesis, because the calculator assumes that you're writing your null in the form of p equals p sub 0. All right. So the short explanation is whatever you put in the null hypothesis, that's what will go there. All right. The x value, 128. The n value, 317. The inequality used in your alternative hypothesis. In this case, we used a not equal to symbol. And then you go to calculate. And so you get good information. I mean, it tells you the z statistic, it tells you the p-value. But the problem is this only will use, or well, at least this hypothesis test only uses this particular formula. If there's an instance where we don't have faith in the population proportion, and we think that the sample proportion is the more appropriate way to go, or there's no way to tell what the assumed population proportion is, we wouldn't have a number to put in for p sub 0, right? So what we would do is we would assume the p hat value. So another variation of this formula is all the same stuff here, just instead of pq over n, it would be p hat q hat over n. In those instances, the calculator is going to let you down. It's not going to give you the correct answer. But if you can assume the p-value that you're using is a reasonable estimate, at least, of the status quo, then you're in good shape. Then you can use the calculator approach. All right, but you still need to show all the steps. So at best, you're going to just use this to check your work. All right. So, and also you'll look at the p-value that we came up with, the 0.307. That's half of what the calculator came up with, because the calculator uses this rule. It doubles the p-value in order to compare it to specifically alpha. All right. So for consistency, you may want to do that, but you can go either way. All right. It's correct either way. Come on, stop doing that. But when you're dealing with a population mean, there's not much different except, well, obviously your formula for computing the test statistics is going to be different, and the notation. You know, it's not p anymore, it's mu. But it still has a one-sided or one-tailed test versus two-tailed test determined by your alternative hypothesis. You're also going to compute a test statistic and a p-value from there, and use that to draw a conclusion. So the structure of it's the same, just a couple of differences along the way. So this is a completely solved example. I'll just take you through one from scratch. Yeah, can at least get started on it. So over the summer, you attend freshman orientation at your future college. While there, the dean of admissions states that average freshman spends $300 on books for the first semester. But when you show up in September, your book bill comes to a lot more than $300. You ask some of the people in your dorm how much they spent on books, and it seems like most of the responses are more than $300. So now you think the dean of admissions figure of $300 is flat out inaccurate, and that the real average is higher than $300. Okay. So you take a simple random sample of 35 individuals, 35 freshmen, and the average amount spent on the books. So 35 individuals, the average was 329 with a sample standard deviation of 19. All right, so that's the summary statistics that we have. We need to make a determination if that projects out to the population in a way that we can conclude that the true average price for textbooks is more than 300. All right, so my null hypothesis is going to be that the average is 300. all right, that the dean isn't lying. The dean's telling the truth. All right, we default to that. All right. Alternatively, we would say that the average is actually more than 300, statistically significantly more than 300. All right. That leads us to a right tail test. We do not know the population standard deviation, so this is going to be a t distribution. We don't know what sigma is. So my critical value is going to be a t-score instead of a z-score. Is your finding enough evidence, or are your findings, I guess, enough evidence to suggest that the average amount spent on books by freshmen is more than 300? They didn't say anything about an alpha value. So we'll let alpha equal 0.05. Whenever you're dealing with a t-distribution, you need to know degrees of freedom. Degrees of freedom is equal to n minus 1. We have n of 35, so 35 minus 1 is 34. So now I go to my calculator to get my inverse t value. No good place to put this. I'll just put it here for the time being. So inverse t, so second vars, option 4. The area that we're concerned with is 0.05. It always gives area to the left, but since it's symmetrical, I could just put in my alpha value with the appropriate degrees of freedom. If it's on the right, I ditch the negative sign. If it's on the left, I keep the negative sign. All right, so 1.691, about. So that would be my cutoff. Now my test statistic, get rid of this for now. It's the same structure. Statistic minus parameter divided by standard error. So test statistic in this context is going to be t equals x bar is my statistic, mu is the parameter, s over the square root of n by central limit theorem is my standard error. All right, so a little number crunching. 329 minus the assumed value for mu, 300. S is 19 over the square root of 35. So we have to crunch this through real quick. All right, so alpha y equals n over d. Well, top number is just 29. Alpha y equals n over d, 19, square root of 35. So huge. Okay, 9.0298. All right. We get the p-value by looking for the probability that t is greater than that 9.0298. So I'll hang on to this. I'll store it as t, capital T. Only real option there. So I'm going to use second vars. And I'm going to use TCDF. The low bound is what I just defined as t. Wherever the heck it is. Okay, there it is. Upper bound, something big. I'll just put in the 1E99 with the appropriate degrees of freedom. Since it's bigger than 34, I'm sorry, bigger than 30, it is 34 degrees of freedom. We're looking at something that could be approximated with a normal distribution just by the size of the sample. But since we don't know the population standard deviation, we tend to go with the t distribution. So we're looking at 7.44. I'll throw a 1 in there. Times 10 to the negative 11th power. Again, if the p-value is less than the alpha value, you would reject the null hypothesis. But also, based off of the diagram, if I were to plot a t-value of 9.0298, right, if I were to plot this on here, it would be like way out over here, squarely in that rejection area. Right? So in either event, we're going to reject the null hypothesis. All right, which means the null hypothesis this time is incorrect. The alternative would be, if it's only the two choices, the alternative would have to be the one that's correct. Right? And so then it's just a matter of writing the full-blown conclusion. So there is sufficient evidence to reject the claim that the population mean amount spent on books is $300 at the 0.05 level. Therefore, the claim that it is more would be true. All right, so we'll pick up with the next example tomorrow. On page 28, we have this example, and it's just a continuation of what we did before. It's just using raw data. So we did a one-sample t-test. All right, so it's a t-distribution. We were comparing means, some previously understood mean to sample statistics that we were provided. All right. Here we're not provided the sample statistics, but we are provided raw data, and we can use that raw data to determine the sample statistics. All right. So Frank has been sensing that his car is not driving right, I guess correctly. He takes his car to the mechanic, who does some testing on the ignition timing. For Frank's car to run at optimum efficiency, the spark plugs need to ignite and spark on average every 1.3 seconds. Assume that the standard deviation of all spark plug firings is known to be sigma is equal to 0.5 seconds. All right, so that's a key ingredient there. Known to be 0.5 seconds. When you know this, the population standard deviation, that makes it a z distribution. All right, so since sigma is known, that's a theta. Use a z distribution. And that's regardless of the size of the sample. All right. So generally with small samples, we go with a t-distribution, but that's usually because with small samples, we don't know the population standard deviation. But if you're given the population standard deviation, then we can assume the normal distribution, or z distribution, as we sometimes call it. All right, mechanic suspects that they're not firing at this optimal interval. The mechanic took a random sample of 30 spark plug ignition firings. As it turns out, it's sufficient for us to use a z distribution. The sample size is 30 or more, and got the following data. So we'd have to put this information in. It's kind of a pain, but the calculator, and I'll show you the hypothesis test function on the calculator in a sec, but the calculator will get you everything you need. It's just we have to show the work, all right? So it's kind of one of those things where, you already know what the answer is going to be based off the calculator, but you still have to sort of go through the motions. Data in. Now I need the mean. I don't need the sample standard deviation because we're assuming the population standard deviation of 0.5. So I need an x bar for the n value of 30. X bar is going to be whatever it ends up being. We'll take a look at that in a second. Sigma is 0.5 seconds. All right, so we could run the numbers in terms of one variable statistics, stat calc, one var stats. We get 1.73 repeated, 1.173 repeated. I'll just throw the repeated on there. All right. It really doesn't matter. I mean, if you go to 3 significant, you could write the 3 significant digits down on paper. We're still going to use the most accurate form in the calculator anyway. All right. So we need a null and alternative, a set of null and alternative hypotheses. The null would be the case that there is no difference between what the population standard deviation was before and what it is now, right? So it's saying that it should fire off every 1.3 seconds, right? That's a long-standing rule or belief, right? So mu would be 1.3. If it's not firing off at that optimal timing, then there would be something wrong. It would be misfiring. It doesn't have to be necessarily more or less than 1.3, just different. All right. So anything different from 1.3 would be a mistiming situation. So mu would be not equal to 1.3. All right. So that's our long-standing rule or belief. We came up with 1.173. If anything, the mean would be less than 1.3 based off of this information. But if all things are equal, it should be 1.3. Right? And so really kind of think about it. It ties together with the idea of just random existence. So when we talked about probability, we talked about things occurring the way they're supposed to occur. Right? So if you flip a coin 3,000 times, what's supposed to occur is that 1,500 of those times you should get heads and 1,500 of those times you should get tails. It doesn't always play out that way. Sometimes you get 1,450 heads and 1,550 tails. What we're trying to determine is if that difference in the sample is sufficient to cast doubt on the fairness of the coin, right? So in this context, 1.3 is our benchmark. So our sample gave a mean of 1.173. Is that different enough from the population mean or the assumed population mean to cast doubt that that population mean is accurate? All right, that what we knew before still holds true. All right, so that's really what the hypothesis test is getting at. So we create our diagram. Poor quality, of course. Shade the fringes because it's a two-tailed test. We need critical values for the z distribution. They said to use an alpha as 0.05. All right, if it's a two-tailed test or two-sided test, sometimes they call it that. That means you're taking that alpha and you're splitting it up over the two sides. So 0.025, 0.025. All right. So I need critical values associated with the 0.025. So for that, we go into second vars inverse norm, 0.025. All right, so negative 1.96 approximately. All right, the AP folks are not interested in calculator speak. All right, I've mentioned this before. So if you write inverse norm, on your test paper, it's like you wrote nothing. All right, they disregard that. All right, but the good thing is you could actually just jump right from the 0.025 to the negative 1.96. All right, so you don't actually have to say what you typed into the calculator. It's assumed that you did something correct. Otherwise, you wouldn't have got the negative 1.96. All right. So I need my test statistic. All right, and that's going to be z is equal to x bar minus mu over sigma over the square root of n. It's the same formula for the t distribution. The only difference is that we have a sigma instead of an s. So that's kind of nice. All right, the consistency there. And also, it's z instead of t, but I think that goes without saying. All right, so we have the 1.173 approximately minus 1.3. I'll put the little repeating bar there. Sigma is 0.5 given. Square root of 30. So we crunch these numbers in their most accurate form in the calculator. The calculator hung on to the x bar from the one variable statistics. So I'm going to type this in, alpha y equals n over d. Vars, option 5, option 2. All right, so that'll just bring up the x bar, but we know that the calculator knows that x bar is 1.73 repeated. All right, so again, that's Vars statistics. All right, and you just find the thing you're looking for. Sometimes you want the standard deviation. In this case, we want the x bar. All right, minus 1.3 over another fraction, but this fraction you could use just the division. Or you could just put a fraction within a fraction. It doesn't matter. It's going to work out the same way. All right. I like to do it for the any cases involving polynomials, binomials, whatever, just because then I don't have to worry about parentheses. All right. But this is satisfactory, and we get negative 1.388 approximately. All right. Again, to find the p-value, we need to work with the most accurate form. You want to work with the most exact form until the very last step when you start drawing conclusions. So I need the p-value based off of the negative 1.387563812, not the negative 1.388. That may introduce an unacceptable amount of variation. All right, so what I can do here is find the probability that z is less than that negative 1.388. All right, it's on the left-hand side, so I'm looking for the area contained between negative 1.388 and the end of time, well, actually the beginning of time, negative infinity. All right, so that would be from here on over. So it's basically saying all of this area. And I would want to know how that compares against the alpha over 2. Right? And I know it's been a while, but the two schools of thought when it comes to a two-tailed distribution or two-tailed test is you can compare this p-value to, or this probability value, I should say, to half of the alpha value, or we can double it, whatever we get here, double it and compare it to alpha itself. All right. Either way, if this value is less than whatever the alpha value is, or alpha over 2, depending, you would reject the null hypothesis. All right, but before we do that, we got to get this number. So I'm going to store. We'll call it z, capital Z. So I'm looking for the area to the left of this. So a second, vars, normal CDF. To the left would be negative infinity to what I just called z. Paste it in, and you get 0.0826. All right. So the question is this probability value less than the alpha over 2? All right? Because this is only giving you one side of the two-sided test, right? And it's not, because alpha over 2 is 0.025, right? So the p z minus less than 1.388 is not less than 0.025. So do not reject the null hypothesis. It always feels like a little bit overkill because the negative 1.388 didn't fall in the rejection area. So my test statistic fell in the non-shaded region, not the shaded region. Shaded region would tell us to reject the null hypothesis. The non-shaded region is telling us not to reject the null hypothesis. So we already knew not to reject the null hypothesis. So it always feels like overkill. But what we're getting at here is essentially, I mean, if we're talking about the alpha values being the probability of making a type 1 error, right? So a type 1 error, again, is mistakenly rejecting the null hypothesis. It's really a cutoff for that. If your alpha value is sufficiently small, like 0.01, 0.05, 0.10, and the p-value that you come up with is even smaller than that, then what we're saying is that the chances, the probability of you mistakenly rejecting the null hypothesis would be minuscule, right? Very tiny. So if you were to reject the null hypothesis, the chances of you doing so mistakenly would be so small that you could say, okay, I'm going to reject the null hypothesis. The chances that I'm wrong in doing so are minute, so I can reject the null hypothesis, right? But if they're not smaller than that benchmark set forth by the alpha value, then we can't say that the probability of mistakenly rejecting the null hypothesis is sufficiently small. So it would be an extreme risk. Well, maybe not extreme. That's a little extreme. It would be too risky to reject the null hypothesis because the probability of doing so incorrectly would be too large. All right. So we would have to draw a conclusion here, but let me show you really quickly how to do this from top to bottom on the calculator, in the calculator. Stat, test, this is a z-test. All right, so stat test option 1. You have an option to input data or stats. We typed in data, so data it is. The mu sub 0 is whatever number you put into the null hypothesis. All right, so that would be 1.3. All right, because the assumption here is that or at least the TI assumption is that this is mu is equal to mu sub 0 as your HO. So whatever we call the mu sub 0, whatever we're letting mu be equal to, that's going to be the null hypothesis. The 60,000 was a holdover from when we did this with the real estate problem for confidence intervals. It just hangs on to stuff till you change it. But we're making that 0.5 now. I have my data in list 1, L1. Not equal to symbol, right? Not equal to in the alternative hypothesis. And then write to calculate. Right? So when you do that, you see that the z statistic, the test statistic, is pretty much what we got. Ours is the rounded form on paper. But the p-value right below that is double what we got. All right? So the p-value is equal to twice the probability. I'll use a multiplication symbol. Z is less than negative 1.388. So you get approximately 16.5%, or you could just say 0.165. So you take this number and double it, that gives you the p-value, right? So if you only go on the one side, you're not coming up with the p-value, but you do have something that you could use to draw a conclusion, right? The idea here is for any two-sided test, You have the either or. Right? So if you're dealing with a not equal symbol, it could either be less than or greater than. All right? Less than whatever the z statistic is, or greater than. Right? So we'd have to account for both sides. And that has to do with, really, it's more like perspective. It doesn't really come up so much when you're dealing with one sample distributions, but when you're dealing with two sample distributions, it becomes more obvious. But the difference between the x bar minus the mu is really subjective. All right, that's kind of a decision that we make. When you're looking for a difference between two values, if I say, what's the difference between my age and your age? You're probably going to come up with the positive value. You know, so if I say the difference between my age and your age, I say I'm 40, 44 this year, and you're 17, 18 years old. Find the difference. You're probably going to do the 44 minus the 17 or 18, come up with a positive number. But in theory, somebody could go the other way around and say the difference between the two numbers is negative, 27 years old. Yeah, it could be positive 27 years old. It could be negative 27 years old. Depends on perspective. All right, so this allows for that to happen. So if you're looking for the difference between two values, the x bar and the mu, it could be positive or it could be negative. We just choose to make it x bar first, then the mu. All right, so that needs to be accounted for. And in a two-sided test, since you know that you have area on both sides, you have to account for the fact that that test statistic could, in theory, also be a positive counterpart. So it could be all of this area and all of this area combined. All right. So the fringes of the test statistic, but only in a two-tailed situation. All right. So to get the p-value, the number to compare against just plain old alpha, you'd have to take both of those areas and add them together. All right. So this is the same. Doing this is the same as saying the probability that z is less than negative 1.388 plus the probability that z is greater than positive 1.388. All right. So in the case of a one-tail test, it really wouldn't matter. You wouldn't have to go on both ends because perspective isn't really as important. Right? Because I could look at it and say, mu is less than 1.3 or mu is greater than 1.3. That's going to put you on one side versus the other, and then the difference in the numerator should be consistent with that decision. Right? So it's a lot of theory, but and honestly, we get into as much theory as we can with hypothesis testing, knowing that we can never really truly understand any of this without integral calculus. Because it's like it all goes back to where these areas came from to begin with. It's the area under a curve. If you have any experience with integration in calculus, the area under a curve comes from that. All right, so that's not something we get into in this course. So there's the basis to understand it isn't going to come until maybe next year, maybe later this year if you're in BC. Maybe already, I don't know. Because I know some people do integration in physics. So either way, you got to kind of wait until you can put all the pieces together. But for now, it's just a matter of saying, okay, where are we getting our areas from and what areas are important? But we also need to know or be able to write a conclusion. So the conclusion template, there is either sufficient or insufficient evidence, depending on your decision to reject the null hypothesis. And then from there, we would state the null hypothesis. We're either going to reject or not. So in this case, we did not reject. So there is insufficient evidence. I'm going to move this down. My hand got in the way. To reject the claim that the population mean timing I mean, if you were writing this up for a journal, or doing a project, you'd be more specific. You would say the population mean spark plug timing. But you have the framing of the question. We know what timing represents now, so we could just say timing. Is 1.3 seconds at the 0.05 level. That would be significance level. All right, so we have to actually answer the question that's being asked, because this sentence only addresses our decision to reject the null hypothesis. Insufficient evidence to reject the claim that the population mean timing is 1.3 seconds at the 0.05 significance level. So then they were asking, based on this data, can we say Frank's car problem stemmed from the spark plug timing? All right, so if there's not enough evidence to reject the claim that the spark plug timing is 1.3 seconds, and 1.3 seconds is considered good as a spark plug timing, then it's probably not the spark plugs that are the problem. So whatever's wrong with this car isn't as simple, or necessarily, as the spark plugs. Right? Maybe it could be the serpentine belt, it could be the alternator, or it could be like a blown transmission, So you don't know, but anytime you diagnose anything, whether it's medical, engineering, mechanical, you always try to eliminate all the simple stuff first, because you don't want to jump to the most extreme cases. Change somebody's engine out, and it turns out that it's just spark plugs. Right? So, but unfortunately for Frank here, he knows that there's a problem with his car, but now he can't say that it's the timing of the spark plugs. So, can we say that Frank's car problems stem from spark plug timing? The answer would be no. Frank's car problems do not stem from spark plug timing. All right, because again, a hypothesis test is really just talking about what a number is supposed to be. You collect data to make a determination of whether that sample will actually support what that number is supposed to be. And again, I always go back to the simple case of like flipping a coin. All right? Sometimes that's a little too simple, because then it's like, well, how does this relate to spark plug timing? But it's really the same idea. Like, for example, I don't know if this is the example I use in the next one. Something similar. But when you get to match pairs, it's a little bit clearer, because if you talked about, I think I mentioned this example with confidence intervals. If you asked a person how tall they were and then actually measured how tall they were, if they're telling the truth about their height as best they know it, the difference between those numbers should be pretty close to zero. So the expected outcome would be an average of zero. All right, you would want to say like, or I think I used GPA at one point. Like, if I tell you my GPA is 3.9, and then you go look up my GPA, if I'm telling the truth, it should be somewhere around 3.9. All right, so the difference between what I said and what it really was should be very close to zero. All right, so we have an expected outcome. We have an idea of what that result should be. But we need to collect information in order to verify that that's the case. So if I were to make the claim that students at John Jay lie about their height, thank you, then I would ask them what their heights are. Then I would also measure their heights and determine if the average difference was equal to zero. But we know it's not going to be exactly equal to zero, because, people round, people misremember, and especially if you're still in the growing phase of your life. Now, me personally, I think I'm in a shrinking phase of my life. So 6'2 3/4", maybe not. spinal compression and all that stuff. Could be 6'2" now for all I know. All right, I haven't actually measured my height in a while, but best I know, in the neighborhood of 6'3". All right, so I tell you that, you say, what's your height? I say about 6'3". Then you measure my height, 6'2". You're going to get a difference of 1 inch. All right, some people are going to overestimate, some people are going to underestimate, some people are going to nail it. But if people are being honest, then on average, the difference between what they say and what the reality is should be very close to 0. But if it's not close to 0, then we could say that they're not being truthful. But how far away is far enough away? That's where the hypothesis test comes into play. All right, because that determines, based off significance, statistical significance, probability, what an appropriate difference from the mean should be. And if you're within that interval, that confidence interval, then you're in good shape. You're not quote unquote lying. All right, but a hypothesis test just gives us, it's very straightforward. It's basically saying true or false. All right, it doesn't even bother with the interval. That's happening behind the scenes. All right, so when you're dealing with the match pairs case, this example was practice AP exam score, actual AP exam score. So if a teacher says, okay, we're going to do some review for the AP exam, I'm going to give you a diagnostic before and after, or maybe I'll just do the diagnostic before and then you take the exam. In theory, you should be looking at an increase in value. All right, so what we're looking to determine here is if the mean of the difference is equal to 0. That would be the null hypothesis. They're saying, test the claim that there is no difference, that the teacher didn't really do such a hot job of preparing the students for the exam, or maybe the student didn't do the work. It could be some mixture of the two things. But alternatively, all I could say is that mean difference is not equal to 0. All right. So this would be the raw data that I would be working with. We don't know the population standard deviation, so this would be a t distribution. All right. We have 31 individuals. Because it's a t distribution, we need degrees of freedom. n-1 for degrees of freedom. All right, this is not a 2-variable situation. It's the same variable, just measured twice. So 31 minus 1 gives you a 30. We're testing this at the 0.01 significance level, so alpha is 0.01. All right, because it's a not equal to symbol, we need a left tail and a right tailed situation simultaneously. So the critical value for t over here and over here. And then we need our test statistic. All right, and so that's going to be t is equal to same setup as the z distribution, x bar minus mu over s over the square root of n, but this is specifically for the difference in scores. So d's as subscripts. All right, and then from there we need a p-value and a conclusion. All right, so that's what I'd like you to try to do for homework. We'll pick up with it tomorrow. I'm not going to ask you to submit. Not this time.